Hello there, and welcome to The Sleepy Scientist, where frozen mysteries meet cozy curiosity, and science takes a gentle journey through time. Tonight, we're embarking on a quiet expedition into one of Earth's most remarkable archives, the ice cores hidden deep within glaciers and ice sheets. These frozen libraries hold secrets that stretch back hundreds of thousands of years, whispering stories of ancient climates, vanished civilizations, and even cosmic events that our planet has witnessed long before any human walked its surface. Before we begin our frosty adventure, I'd love to know where in the world you're listening from tonight and what season you're experiencing right now. Are you bundled up in winter's embrace? Or perhaps enjoying a warm summer evening? It's fascinating, isn't it? How we're all experiencing different temperatures, different weather patterns at this very moment. Yet the ice we'll explore tonight has been faithfully recording these variations for millennia. If you find this chilly voyage through time soothing or intriguing, I'd be ever so grateful if you gave the video a gentle like and maybe subscribed it. Helps this little corner of scientific serenity reach others who might need a peaceful pause in their day. Now, I do hope this isn't so captivating that it keeps you awake, but if it does well, at least you'll drift off, knowing something extraordinary about the frozen time capsules beneath our feet. So settle in, take a deep breath, and let's begin, because somewhere between the surface of a glacier and its ancient depths lies a story more intricate than any library, more detailed than any history book, and more beautiful than any work of art ever created. Imagine, if you will, holding a piece of ice in your hands, not just any ice, but a fragment pulled from deep within a glacier. This seemingly simple frozen water has been locked away for perhaps 50,000 years. Maybe more. Within its crystalline structure are tiny bubbles of ancient air, microscopic particles of dust, and even traces of volcanic ash from eruptions that happened when our ancestors were just beginning to discover fire. Ice cores are essentially nature's own filing system, a meticulous record keeper that never takes a day off every year as snow falls and compresses into ice. It captures a snapshot of that moment in Earth's history. The air we breathe, the dust in the atmosphere, the chemical signatures of seasons passing all of it, gets sealed away like a message in a bottle. Except this bottle is made of ice, and the message spans geological time. The process begins quite simply with snowfall, but not just any snowfall. We're talking about snow that falls in places so cold, so remote that it never fully melts. Places like Antarctica and Greenland, where temperatures remain below freezing year round. As each layer of snow accumulates, it slowly compresses under its own weight, gradually transforming from fluffy snow to dense granular ice, and eventually to the clear blue ice we associate with ancient glaciers. This transformation takes time, decades, or even centuries depending on the location, but once that ice forms, it becomes incredibly stable. A frozen archive that can preserve information for hundreds of thousands of years. Some of the oldest ice cores we've extracted contain ice that formed when our planet looked very different, when sea levels were lower, when vast ice sheets covered much of North America and Europe, when the Sahara Desert was green and lush. But what exactly are scientists looking for when they drill these cores? What secrets lie hidden in what appears to be nothing more than frozen water? The answer is both simple and profound. Everything the ice contains tiny air bubbles that hold samples of ancient atmospheres, telling us exactly what the air was like. Thousands of years ago, we can measure carbon dioxide levels, methane concentrations, even the isotopic composition of oxygen to understand past temperatures. The dust and particles trapped within the ice tell us about volcanic eruptions, massive forest fires, and even cosmic events like meteor impacts. The chemical composition reveals seasonal patterns, ancient weather systems, and long term climate shifts. It's like having a detailed weather report for every year stretching back through human history and beyond into the deep geological past. When scientists extract these cores, they're essentially performing archaeological surgery on time itself. The process requires incredible precision and care. The drilling must be done in the coldest, most remote places on Earth, often in conditions that would challenge even the most experienced polar explorers. Temperatures can drop to minus 40 degrees Fahrenheit, or colder winds can reach hurricane force, and the nearest civilization might be thousands of miles away. The drilling itself is a marvel of engineering. A specialized drill bit slowly works its way down through hundreds or even thousands of feet of ice. Each section that comes up is carefully cataloged, measured, and preserved. The cores are then transported in refrigerated containers to laboratories around the world where scientists can begin the painstaking process of analysis. Reading an ice core is like reading the rings of an ancient tree, except instead of counting years, you're counting layers of compressed snow. Each layer represents 1 year of accumulation, and within that layer is a wealth of information about what was happening on Earth at that time. The thickness of the layer tells us about snowfall patterns. The color and clarity reveal information about atmospheric conditions, and the chemical composition provides detailed data about temperature, humidity, and atmospheric gases. One of the most remarkable things about ice cores is their incredible resolution. While other geological records might give us information about climate changes over thousands or millions of years, ice cores can provide annual or even seasonal data stretching back hundreds of thousands of years. It's like having a high definition photograph of Earth's climate history compared to the blurry snapshots provided by other methods. The air bubbles trapped in ice cores are particularly fascinating. These tiny pockets of ancient atmosphere are like time capsules containing the exact mixture of gases that existed when that ice formed by analyzing these bubbles. Scientists can determine atmospheric carbon dioxide levels from thousands of years ago. They can measure methane concentrations and even detect trace gases that provide clues about ancient ecosystems. What's truly mind boggling is the level of detail these cores provide. They can tell us not just about average conditions over long periods, but about rapid changes, sudden climate shifts that happened over just a few years, or even a single season. Some ice cores have revealed evidence of climate changes so rapid and dramatic that they would have been almost unimaginable to witness. For instance, scientists have found evidence in Greenland ice cores of temperature changes of 10 degrees Celsius or more happening within a single decade. These weren't gradual shifts over centuries, but sudden dramatic changes that would have completely transformed entire ecosystems. Imagine going from a relatively mild climate to something resembling an ice age in just a few years. The dust and particles in ice cores tell equally fascinating stories. Volcanic eruptions leave distinctive signatures in the ice. The sulfur compounds and ash from major eruptions can be detected in cores from around the world, allowing scientists to date and study volcanic events from thousands of years ago. Some of the largest volcanic eruptions in human history have left their mark in ice cores from both poles. Even more intriguingly, ice cores contain evidence of cosmic events, meteor impacts, and even changes in solar activity leave subtle but detectable signatures in the ice. The 1908 Tunguska event in Siberia, where a meteor or comet exploded in the atmosphere, has been detected in ice cores. The cosmic dust and unusual isotopes created by this event were captured and preserved, providing a frozen record of this extraordinary occurrence. But perhaps the most humbling aspect of ice core research is what it reveals about the stability of our climate. The ice cores show us that Earth's climate system is far more dynamic and changeable than we might expect. Periods of relative stability are punctuated by rapid, sometimes catastrophic changes that reshape entire continents. The Little Ice Age, a period of cooling that occurred from roughly the 14th to the 19th centuries, is clearly visible in ice cores from around the world. This period saw advancing glaciers, failed harvests, and significant social upheaval across Europe and North America. The ice cores not only confirm that this cooling occurred, but provide detailed information about its timing, intensity, and regional variations on longer timescales. Ice cores reveal the ice ages themselves, the great glacial and interglacial periods that have dominated Earth's recent geological history. These cycles, driven by changes in Earth's orbit around the Sun, are written in exquisite detail in the deepest ice cores. Each ice age and the warming period that followed left its signature in the ice. Tonight, as you drift toward sleep, perhaps you'll dream of these frozen archives. Imagine the stories they could tell if they could speak. The ancient storms, they've weathered the slow dance of seasons. They've recorded the volcanic winters and cosmic summers they've witnessed. They are silent witnesses to the grand epic of our planet's history, patient and eternal keepers of secrets that stretch back through time, immemorial. The stories held within these frozen time capsules become even more extraordinary when we consider how scientists decode them. It's not simply a matter of melting the ice and examining what's left. The process is far more intricate, like learning to read a language written in crystals and chemistry. When a fresh ice core arrives at a laboratory, it's treated with the reverence of an ancient manuscript. Each section is photographed, documented, and stored in freezers that maintain temperatures well below what your kitchen freezer could manage. The analysis begins with something deceptively simple: visual inspection. Scientists examine the ice under special lighting, looking for layers, annual bands that mark the passage of years, much like tree rings, but instead of wood, they're reading compressed snow. The clarity of the ice tells its own story. Clear blue ice indicates clean atmospheric conditions, while cloudy or milky sections suggest periods of high dust, volcanic activity, or rapid temperature changes. Some layers contain visible particles, dark specks that might be dust from distant deserts or ash from volcanic eruptions that occurred thousands of miles away. These visual clues provide the first hints about what was happening in the atmosphere when that particular layer formed. But the real secrets emerge through chemical analysis. Tiny samples are carefully extracted from different layers, and subjected to sophisticated instruments that can detect concentrations of gases and elements at levels measured in parts per billion. It's like having a chemical fingerprint of ancient atmospheres, more detailed than any modern weather station could provide. One of the most remarkable techniques involves analyzing the isotopes of oxygen trapped in the ice. Isotopes are atoms of the same element, with different numbers of neutrons, and their ratios in ice cores provide incredibly precise information about past temperatures when water evaporates from the ocean. It preferentially takes lighter isotopes with it. The ratio of heavy to light oxygen isotopes in ice depends on temperature, so by measuring these ratios, scientists can determine not just whether it was warm or cold, but exactly how warm or cold with precision that would make modern meteorologists envious. The trapped air bubbles present their own fascinating puzzle. These aren't just random pockets of air, but carefully preserved samples of ancient atmospheres. However, there's a curious time lag. The ice forms from compressed snow, but the air bubbles still don't get sealed in immediately. They remain connected to the surface atmosphere for several decades as the snow slowly transforms to ice. This means the air in any given bubble is typically younger than the ice surrounding it, creating a complex timeline that scientists must carefully decode. When researchers want to extract these ancient air samples, they use a technique that sounds almost medieval. They place the ice in a vacuum chamber and crush it. The air bubbles pop, releasing their ancient contents into instruments that can measure gas concentrations with extraordinary precision. Suddenly, we can know exactly how much carbon dioxide was in the atmosphere 5,000 years ago, or what methane levels were like during the Roman Empire. The chemical signatures in ice cores have revealed climate changes so rapid they challenge our understanding of how Earth's systems work. The Younger Dryas period, about 12,000 years ago, saw temperatures in the North Atlantic region drop by several degrees in just a few decades, then snap back to warmer conditions equally quickly. These weren't gradual transitions, but climate whiplash that would have been devastating to any civilizations unlucky enough to experience it. Dust layers and ice cores tell stories of their own, providing evidence of ancient droughts, massive sandstorms, and changing wind patterns. Dust from the Sahara Desert has been found in Greenland ice cores, blown thousands of miles, by ancient atmospheric circulation patterns that were different from today's. The size and composition of dust particles reveal not just where they came from, but what the climate was like in their regions of origin. Volcanic eruptions leave particularly dramatic signatures in ice cores. Major eruptions inject sulfur compounds high into the atmosphere, where they form tiny particles that reflect sunlight back to space, cooling the planet. These volcanic signatures appear in ice cores as spikes in sulfur concentration, often accompanied by evidence of the cooling that followed the 1815 eruption of Mount Tambora in Indonesia's caused global cooling that led to crop failures and famine. The following year was known as the Year Without a Summer, and this event is clearly recorded in ice cores from both poles. Some of the most intriguing discoveries in ice cores involve evidence of human activity long before the Industrial Revolution. Lead pollution from Roman silver mining appears in Greenland. Ice cores showing that human activities were already affecting the atmosphere. 2,000 years ago, the rise and fall of civilizations can sometimes be tracked through changes in atmospheric composition as populations grew, shrank, or shifted their activities. The medieval warm period, roughly from 950 to 1250 CE, shows up clearly in ice cores as a time of relatively mild temperatures across much of the North Atlantic. This warming coincided with Viking expansion into Greenland and North America and may have contributed to agricultural prosperity across Europe. The subsequent cooling that led to the Little Ice Age is equally well documented, with evidence of advancing glaciers, harsh winters, and social disruption. But ice cores also reveal natural climate variations that dwarf anything in recorded human history. The medieval warm period and Little Ice Age were minor blips compared to the dramatic swings between ice ages and interglacial periods. These massive climate cycles, driven by subtle changes in Earth's orbit around the Sun, are written in ice cores stretching back hundreds of thousands of years. The Dansgaard-Oeschger events, named after the scientists who discovered them, are perhaps the most unsettling climate phenomena revealed by ice cores. These were rapid warming and cooling cycles that occurred throughout the last ice age, particularly in the North Atlantic region. Temperatures would rise dramatically within decades, stay elevated for centuries or millennia, then crash back down equally quickly. These events happened dozens of times during the last ice age, suggesting that rapid dramatic climate change might be more common than we'd like to believe. Even more mysterious are the Bond event's longer term cooling cycles that occurred roughly every 1500 years during the Holocene, our current interglacial period. These subtle but persistent cooling events affected civilizations around the world and may have contributed to the collapse of several ancient societies. The causes of these cycles remain poorly understood, but their regular occurrence suggests some kind of internal rhythm in Earth's climate system. The resolution of ice core records varies depending on location and age. The most recent centuries can be read almost year by year, while older sections might represent decades or centuries per layer. But even at lower resolution, the detail is extraordinary. We can see evidence of multi-year droughts, decade-long cold snaps, and the gradual warming that ended ice ages. Some ice cores contain evidence of truly catastrophic events. The Toba supervolcanic eruption about 74,000 years ago left a massive signature in ice cores from around the world. This eruption may have caused a volcanic winter that lasted several years and could have brought early human populations to the brink of extinction. The ice cores provide not just evidence that this event occurred, but detailed information about its global impact and duration. As you lie there tonight, drifting toward sleep, consider the patient ice deep beneath the surface of Greenland and Antarctica, still accumulating, still recording, still preserving the story of our planet's ever-changing climate. Tomorrow's weather will become part of that record, adding another thin layer to an archive that has been building for hundreds of thousands of years. Each snowflake that falls in these remote places carries with it the chemical signature of our current atmosphere, destined to become part of the frozen library that future scientists will read to understand our time. The ice cores remind us that Earth's climate is not a stable, unchanging backdrop to human civilization, but a dynamic, ever-shifting system capable of dramatic, sudden changes that can reshape continents and alter the course of history. They are windows into deep time, revealing a planet that is far more variable and dynamic than our brief human experience might suggest. In these remote polar laboratories, scientists have discovered something even more remarkable than individual climate events. They've found evidence of what researchers call climate tipping points, moments when Earth's entire climate system reorganizes itself into a completely different state. These aren't gradual transitions, but sudden, dramatic shifts that can happen within a human lifetime, transforming the world in ways that would be almost impossible to imagine. One of the most fascinating aspects of ice core research is how it reveals the interconnectedness of our planet's systems. A volcanic eruption in Indonesia affects temperatures in Greenland, dust storms in Asia, influence rainfall patterns in South America, and changes in ocean currents alter weather patterns across entire continents. The ice cores show us that Earth operates as a single integrated system where events in one region can trigger cascading effects around the globe. The technological advances in analyzing ice cores have been nothing short of revolutionary. Early researchers could measure basic chemistry and count annual layers, but modern instruments can detect individual molecules, measure isotope ratios with extraordinary precision, and even analyze the DNA of ancient microorganisms trapped in the ice. It's like upgrading from a magnifying glass to an electron microscope. Suddenly, details that were invisible become crystal clear. Some of the most surprising discoveries have come from studying the smallest components of ice cores, microscopic particles that tell stories of ancient ecosystems. Pollen grains, blown thousands of miles from their source, reveal what plants were growing in distant regions centuries ago. Spores from fungi and bacteria provide clues about soil conditions and vegetation changes. Even tiny fragments of charcoal tell us about ancient wildfires, their frequency, intensity, and the types of forests that burned. The seasonal variations preserved in ice cores create a kind of ancient calendar that's more reliable than any human record scientists can identify. Spring dust storms, summer pollen deposits, autumn organic matter, and winter's cleaner snow layers. This seasonal record allows researchers to understand not just annual averages, but the rhythm of ancient years, the timing of seasons, and how they changed over time. Perhaps most intriguingly, ice cores have revealed that our current climate, the stable conditions that have persisted throughout human civilization, may be unusual rather than normal. For most of the last 100,000 years, Earth's climate was far more variable, with rapid switches between different states. The Holocene period, during which all of human agriculture and civilization developed, represents an unusually stable interval in Earth's climate history. This stability may be more fragile than we realize. Ice cores show that in the past, relatively small changes in atmospheric composition or ocean circulation have triggered massive climate reorganizations. The Younger Dryas period began when melting ice sheets disrupted ocean currents, causing temperatures across the North Atlantic to plummet within decades. It's a sobering reminder that the climate system has tipping points beyond which change becomes rapid and irreversible. The chemistry preserved in ice cores also reveals the natural background levels of atmospheric gases. Before human influence, carbon dioxide levels fluctuated naturally over geological time, but stayed within a relatively narrow range. For thousands of years, methane concentrations rose and fell with changing wetland areas and vegetation patterns. These natural baselines provide crucial context for understanding modern atmospheric changes. Some ice cores contain what scientists call the Anthropocene signal, the chemical fingerprint of human civilization. This signal begins subtly with traces of lead from ancient metallurgy and gradually intensifies through the Industrial Revolution. The most dramatic changes appear in the most recent layers, where greenhouse gas concentrations spike to levels not seen in hundreds of thousands of years. The preservation of organic compounds in ice cores has opened entirely new avenues of research. Scientists can now extract and analyze ancient DNA from ice cores, revealing which species of plants, animals, and microorganisms were present in past climates. This biological information adds another dimension to our understanding of how ecosystems responded to climate changes, providing insights that could help predict how modern ecosystems might adapt to future changes. Wind patterns preserved in ice cores tell their own remarkable stories. The direction and strength of prevailing winds affected how dust, volcanic ash, and other particles were distributed around the globe. By analyzing the chemical composition and size distribution of particles in ice cores, scientists can reconstruct ancient wind patterns, revealing how atmospheric circulation has changed over time. The deepest ice cores, those extending back hundreds of thousands of years, reveal the full scope of Earth's climate variability. They show ice ages that lasted tens of thousands of years, punctuated by brief, warm periods, like our current interglacial. These long-term cycles are driven by changes in Earth's orbit around the Sun. But the ice cores reveal that the climate response to these orbital changes is far from simple, involving complex feedbacks between ice sheets, ocean's atmosphere, and vegetation. Studying ice cores has also revealed the existence of climate phenomena that no longer occur. Massive ice sheets that covered much of North America and Europe behaved in ways that have no modern analog. These ice sheets grew and shrank according to their own complex dynamics, sometimes advancing rapidly across continents, and sometimes collapsing catastrophically, raising sea levels by hundreds of feet. The technology for extracting ice cores continues to evolve. New drilling techniques allow scientists to reach ever greater depths while maintaining the integrity of the ice. Advanced preservation methods ensure that samples remain uncontaminated during transport and storage. Sophisticated analytical instruments can measure ever smaller concentrations of trace compounds, revealing details about past climates that would have been unimaginable just decades ago. Some of the most remote ice core sites are located in places so isolated that reaching them requires months of planning and preparation. Scientists must transport heavy drilling equipment across hundreds of miles of ice and snow, working in conditions where the slightest mistake could be fatal. The dedication required for this research is extraordinary, with teams spending months in polar darkness, enduring temperatures that would kill an unprotected person within minutes. The international cooperation required for ice core research represents science at its best. Teams from dozens of countries work together, sharing data techniques and insights. The ice cores themselves are often shared between laboratories, allowing multiple research groups to analyze different aspects of the same samples. This collaborative approach has accelerated discoveries and ensured that these precious climate archives are studied with the most advanced techniques available. As you settle deeper into sleep tonight, Imagine the quiet laboratories where scientists carefully examine these frozen messengers from the past. Picture the moment when a researcher first notices an unusual layer in an ice core or discovers evidence of a previously unknown climate event. These moments of discovery connect us directly to our planet's deep history, revealing secrets that have been locked away for millennia. The stories told by ice cores are ultimately stories about change, about a planet that is constantly evolving and transforming. They remind us that the Earth we know today, with its familiar climate patterns and seasonal rhythms, is just one moment in a much longer story of transformation. The ice cores whisper of ancient worlds, where the Sahara was green, where massive lakes covered what is now desert, where ice sheets advanced and retreated like slow breathing across the continents. In the gentle darkness of your bedroom, you're connected to these frozen archives through the very air you breathe. The oxygen in your lungs carries isotopic signatures that future ice cores will preserve. The carbon dioxide you exhale will mix in the global atmosphere and eventually find its way into the ice sheets of Greenland and Antarctica, where it will become part of the record that future scientists will study to understand our time. The ice cores teach us patience. They formed grain by grain, layer by layer, over thousands of years. Yet they can record changes that happened faster than human memory could preserve. They are simultaneously records of gradual transformation and sudden catastrophe, of the slow accumulation of seasons and the rapid reorganization of entire climate systems. Somewhere far beneath your feet, if you could tunnel through rock and magma and emerge on the other side of the world, you might find yourself standing on the Antarctic ice sheet, where even now snow is falling and compressing into ice that will preserve the chemical signature of today's atmosphere for future millennia. To discover that ice cores are still being written, still accumulating, still faithfully recording the ongoing story of our planet's climate. Perhaps most remarkably, the ice cores have revealed that our planet has its own memory, a kind of climatic consciousness that carries the echoes of past events forward through time. When massive volcanic eruptions inject sulfur into the stratosphere, the cooling effects can persist for years, but the ice cores show us something even more intriguing. These events can trigger feedback loops that influence climate patterns for decades or even centuries afterward. The chemical conversations recorded in ice cores tell us about the delicate balance between Earth's carbon cycle and its climate system. During ice ages, atmospheric carbon dioxide levels dropped to concentrations that pushed plant life to its very limits. Yet somehow ecosystems adapted and survived when the ice ages ended. Carbon dioxide levels rose again, but not always smoothly. The ice cores reveal periods of rapid carbon cycling where atmospheric concentrations fluctuated wildly, as if the planet itself was struggling to find a new equilibrium. Some ice cores contain evidence of what scientists call climate flickering periods, when the climate system seemed unable to settle into any stable state. Temperatures would rise and fall erratically. Precipitation patterns would shift unpredictably, and atmospheric composition would fluctuate like a radio signal, trying to find the right frequency. These flickering periods often preceded major climate transitions, suggesting that instability itself might be a warning sign of impending change. The microscopic world preserved in ice cores reveals secrets about ancient life that no other archive can provide tiny fragments of ancient insects blown onto ice sheets. By prehistoric storms, preserve DNA that tells us about species that lived thousands of years ago. Even bacterial communities, frozen in the ice, maintain enough genetic material to reveal information about ancient ecosystems and how they responded to climate changes. Reading ice cores requires a kind of detective work that combines chemistry, physics, biology, and climatology. Scientists must consider not just what they find in the ice, but how it got there. Understanding wind patterns, precipitation chemistry, and the complex processes that transform snow into ice. Each measurement must be interpreted in the context of dozens of other factors, creating a puzzle where every piece must fit perfectly. The temporal resolution of ice cores varies dramatically depending on location and climatic conditions. In some areas where snowfall is heavy and consistent, scientists can identify individual storms and weather events in others. Where accumulation is slower, each layer might represent several years of compressed time learning. To read these different temporal signatures requires years of training and an almost intuitive understanding of how ice forms under different conditions. One of the most haunting discoveries in ice core research involves evidence of abrupt ecosystem collapses periods when entire biological communities disappeared within decades, leaving only chemical traces in the ice. These collapses often coincided with rapid climate changes, suggesting that ecosystems have breaking points beyond which they cannot adapt quickly enough to survive the implications for our modern world. Where climate change is happening faster than many natural systems can respond are sobering. The art of ice core chronology, establishing accurate dates for different layers, requires combining multiple techniques. Scientists count annual layers like tree rings, but they also use reference points, volcanic eruptions, with known dates, cosmic ray events, and even correlations with other climate records. The most skilled chronologists can establish dates accurate to within a few years for ice that formed thousands of years ago. Some of the most valuable ice cores come from the most unlikely places, high altitude tropical glaciers that preserve unique records of climate conditions in regions where few other paleoclimate archives exist. These tropical ice cores reveal how climate changes affected some of the most biodiverse regions on Earth, showing connections between high altitude glaciation and lowland rainforest ecosystems. The drilling of ice cores has become increasingly sophisticated, with techniques that can extract continuous records from depths exceeding 2 miles below the surface. Specialized drilling fluids prevent the borehole from collapsing, while diamond tipped drill bits cut through ice that has been compressed under enormous pressure for hundreds of thousands of years. The cores that emerge are like perfectly preserved books waiting to be read. Laboratory analysis of ice cores requires facilities that maintain temperatures colder than most natural freezers. Specialized clean rooms prevent contamination, while instruments capable of measuring individual atoms detect trace compounds at concentrations measured in parts per trillion. The precision required for this work pushes the boundaries of analytical chemistry, creating techniques that often find applications in other fields of science. The global network of ice core researchers shares data through international databases, allowing scientists anywhere in the world to access information from cores drilled in remote polar regions. This collaboration has accelerated discoveries and ensured that these irreplaceable climate archives are studied with the most advanced techniques available. The ice cores belong not to any single nation, but to all of humanity. As you drift deeper into the realm of dreams tonight, perhaps you'll visit these frozen libraries in your sleep, walking through tunnels carved from compressed snow, examining layers that formed when your ancestors were discovering fire or agriculture or writing the ice cores connect us to deep time, reminding us that we are part of a story much larger and longer than any individual human life. The patience required for ice core research mirrors the patience of the ice itself. Scientists often spend years planning expeditions, months in the field, extracting cores, and additional years analyzing the results. This slow, careful approach to understanding matches the gradual accumulation of the ice itself, where each layer represents not just a moment in time, but a patient process of preservation. Some ice cores contain surprises layers that don't fit expected patterns, chemical signatures that suggest unknown events, or climate phenomena that challenge our understanding of how Earth's systems work. These anomalies often lead to the most important discoveries, forcing scientists to reconsider their assumptions and develop new theories about how climate and environment interact. The deepest ice cores reach back through multiple ice ages, revealing climate cycles that dwarf anything in human experience. These ancient records show that ice ages and warm periods follow patterns related to Earth's orbital cycles, but with complex variations that suggest the climate system has its own internal rhythms and feedback mechanisms. Modern ice cores. The layers forming today will someday tell future scientists about our current era. They will see evidence of industrial pollution, nuclear weapons testing, and the dramatic increase in greenhouse gases that characterizes the Anthropocene epoch. In a sense, we are all contributing to the ice core record that future generations will study to understand our impact on the planet. The stories preserved in ice cores remind us that Earth is not a static stage for human activities, but a dynamic, ever changing system capable of dramatic transformations that can reshape continents and alter the course of life itself. They are windows into deep time, revealing a planet far more variable and dynamic than our brief human experience might suggest. In the quiet darkness of your room, you are connected to these ancient archives through the very atoms in your body. The oxygen you breathe, the carbon in your cells, all participate in cycles that have continued for millions of years and will continue long after we are gone. The ice cores teach us humility, showing us our place in the vast sweep of geological time tonight as sleep approaches. You let your mind wander to those remote ice sheets where snow continues to fall and compress, carrying forward the chemical signature of our current atmosphere into the frozen libraries of the future. Somewhere in the darkness of polar night drilling crews work by artificial light extracting cores that will reveal secrets about climates that existed before humans walked the earth. The whispered secrets of ice cores speak of a planet in constant conversation with itself, where changes in one region ripple across continents and through time, where the past informs the present and the present shapes the future. They remind us that we are temporary visitors on a world that has been changing and adapting for billions of years, long before we arrived, and will continue long after we are gone. The ice cores have taught us something profound about silence. Not the absence of sound, but the presence of stories waiting to be heard. In the deepest, oldest sections of these frozen archives lie records of climates so ancient they predate the evolution of modern humans by hundreds of thousands of years. Those sections contain evidence of ice ages that lasted for millennia, of warm periods when hippos wallowed in what is now the Thames River, and of atmospheric conditions so different from today that they seem like records from an alien planet. When scientists first began extracting ice cores in the early 20th century, they had little idea of the treasure trove they were unlocking. Early researchers were simply trying to understand how glaciers formed and moved. But as analytical techniques improved and drilling technology advanced, it became clear that these frozen cylinders contained the most detailed climate record ever discovered. Each core was like opening a time capsule that had been sealed away for geological ages. The process of interpreting ice cores requires a kind of scientific poetry, combining hard data with intuitive understanding of natural processes. A single measurement might reveal atmospheric temperature, but understanding what caused that temperature change requires considering volcanic activity, solar variations, ocean currents, and atmospheric circulation patterns. It's detective work on a planetary scale where clues are measured in parts per billion and evidence spans hundreds of thousands of years. Some of the most extraordinary discoveries have emerged from comparing ice cores from different locations. When researchers analyze cores from both Greenland and Antarctica, they can see how climate changes propagated around the globe. Sometimes changes that began in one hemisphere took decades or centuries to influence the other hemisphere, but occasionally climate shifts were so dramatic that they affected the entire planet simultaneously. The chemical fingerprints preserved in ice cores have revealed events that no human ever witnessed: massive volcanic super eruptions that plunged the world into years long volcanic winters, asteroid impacts that filled the atmosphere with debris, and cosmic dust storms from distant supernovas that altered the chemistry of Earth's upper atmosphere. These cosmic events left their signatures in the ice, where they wait patiently for scientists to decode their messages. Studying ice cores has also revealed the remarkable resilience of life on Earth, even during the most extreme climate events preserved in the ice. There is evidence that ecosystems adapted, survived, and eventually flourished again. Bacterial communities found their way to survive in conditions that would seem impossibly harsh. Plant life persisted through ice ages that lasted tens of thousands of years, and somehow biodiversity managed to recover from catastrophic climate changes that would seem unsurvivable. The technology for analyzing ice cores continues to evolve at an extraordinary pace. Instruments that once required samples the size of ice cubes can now extract meaningful data from crystals smaller than grains of rice. Mass spectrometers can detect individual molecules, while electron microscopes reveal the internal structure of ice crystals that formed under ancient atmospheric conditions. These technological advances mean that existing ice cores continue to yield new discoveries decades after they were first extracted. One of the most beautiful aspects of ice core research is how it connects us to the rhythms of our planet. The seasonal layers visible in fresh cores reflect the eternal cycle of winter and summer that has continued unbroken for hundreds of thousands of years, Even during the most extreme climate events, the seasons continued their ancient dance, sometimes shifted in timing or intensity, but never completely disrupted. This constancy provides a reassuring thread of continuity through the dramatic changes recorded in the deeper layers. The air bubbles trapped in ice cores represent perhaps the most direct connection we have to ancient atmospheres. When a scientist crushes a piece of ice to release these bubbles, they are literally breathing air that was trapped when woolly mammoths roamed the earth. The chemical composition of this ancient air provides precise measurements of atmospheric gases from long before any human recorded weather observations. Some ice cores contain evidence of rapid climate oscillations that occurred on timescales almost too fast to believe temperatures that shifted by several degrees within a single decade, precipitation patterns that changed dramatically from one year to the next, an atmospheric circulation that reorganized itself in ways that would have been devastating to any agricultural society unlucky enough to experience them. The deeper sections of ice cores reveal climate cycles that operate on timescales far longer than human civilization. The great ice age cycles, driven by subtle changes in Earth's orbit around the Sun, are written in these frozen archives with a detail and precision that allows scientists to understand not just when ice ages occurred, but how they developed, evolved, and eventually ended. Studying ice cores has revealed that our current interglacial period, the Holocene during which all of human civilization has developed, may be ending soon. In geological terms, the natural cycle suggests that Earth should be cooling toward the next ice age, but human activities have introduced new variables into the climate system that make predictions about the future increasingly complex. The preservation of organic compounds in ice cores has opened extraordinary windows into ancient ecosystems. Scientists can now extract and analyze ancient pollen, revealing what plants were growing thousands of years ago in regions that are now completely different. Microorganisms preserved in the ice tell stories about ancient soil conditions and vegetation patterns, while chemical signatures from ancient forests provide information about prehistoric fire patterns and ecosystem health. Some of the most remote ice core drilling sites require expeditions that push human endurance to its limits. Teams must transport tons of equipment across hundreds of miles of ice, working in conditions where the margin for error is essentially zero. A broken drill bit or contaminated sample can mean months of work are lost, while a single mistake in logistics could strand researchers in places where rescue might be impossible. The international cooperation required for ice core research represents science at its most collaborative cores. Drilled by one nation are often analyzed by researchers from dozens of countries. Techniques developed in one laboratory are shared freely with colleagues around the world, and databases of ice core data are accessible to any scientist who needs them. This spirit of cooperation has accelerated discoveries and ensured that these irreplaceable climate archives are studied with the most advanced methods available. As you settle deeper into the embrace of sleep tonight, let your mind wander to those patient ice sheets where layers continue to accumulate grain by grain, recording the chemical signature of today's atmosphere for future scientists to discover the ice cores. Teach us that we are part of a story much larger than ourselves, a story written in crystals and chemistry that stretches back through deep time. The preservation process that creates ice cores is so reliable that scientists can sometimes identify individual weather events from thousands of years ago, a particularly severe winter storm, a drought that lasted several seasons, or a volcanic eruption that affected weather patterns for years afterward, all leave their distinctive signatures in the ice, waiting to be discovered by researchers with the right tools and knowledge. Some ice cores contain what researchers call climate surprises, evidence of phenomena that don't fit our current understanding of how Earth's climate system works. These anomalies often point toward new discoveries, forcing scientists to reconsider their assumptions about how atmosphere, ocean, and ice interact on both short and long timescales. The chemistry preserved in ice cores reveals not just what happened in ancient climates, but how quickly changes occurred. Some climate transitions that scientists once thought took centuries or millennia actually happened within decades or even years. These rapid changes challenge our understanding of climate stability and suggest that Earth's climate system may be more sensitive to small perturbations than previously believed. Modern analytical techniques can extract information from ice cores that would have seemed like magic to early researchers. Isotope ratios that reveal ancient temperatures with precision measured in fractions of degrees, trace gases that indicate ancient atmospheric chemistry, and even genetic material from organisms that lived thousands of years ago, all preserved in what appears to be simple, frozen water. The deepest ice cores reach back through multiple, complete climate cycles, revealing patterns and relationships that only become visible when viewed across hundreds of thousands of years. These long term records show that climate change is not unusual, but rather a constant feature of Earth's history. Though the rate and magnitude of current changes may be unprecedented in the geological record, studying ice cores requires a patience that matches the patience of the ice itself. Researchers often spend years planning expeditions, months extracting cores, and additional years analyzing results. This deliberate, careful approach mirrors the gradual accumulation of the ice, where each layer represents not just a moment in time, but a slow, patient process of preservation and recording. The stories told by ice cores remind us that Earth operates on timescales that dwarf human experience, while we worry about weather patterns that change from season to season. The ice cores record climate patterns that unfold over millennia. They provide perspective on our place in the vast sweep of geological time, showing us that we are temporary visitors on a planet that has been changing and evolving for billions of years. In the gentle darkness of your room, you are connected to these frozen archives through the very air you breathe. The carbon dioxide you exhale will eventually find its way into the atmosphere, where it may be captured by falling snow on some distant ice sheet, becoming part of the record that future scientists will study to understand our time. Just as we study ancient atmospheres preserved in ice that formed long before humans walked the earth, the ice cores whisper of a planet in constant conversation with itself, where changes ripple across continents and through time, where volcanic eruptions in one hemisphere affect weather patterns in another, where the slow rhythm of ice ages provides a steady beat beneath the more rapid fluctuations of shorter climate cycles. Tonight, as you drift towards sleep, let your imagination carry you to those remote drilling sites where scientists work under the midnight sun, or in polar darkness, extracting cores that connect us directly to our planet's deep past. These frozen messengers from ancient times remind us that we are part of something much larger than ourselves, participants in a climate story that began long before we arrived and will continue long after we are gone. Somewhere in the darkness of a polar night, drilling equipment hums quietly as researchers extract another section of ice that formed when the world was young, when ice sheets covered continents that are now temperate, when the Sahara was green and lush, and when our ancestors were just beginning to discover the power of fire. The ice remembers it all, waiting patiently in its frozen silence to share its secrets with anyone curious enough to listen. The whispered stories of ice cores speak across the centuries, connecting us to climates we never experienced, to atmospheric conditions that existed before any human drew breath. They are letters from the deep past, written in a language of chemistry and crystals that scientists are still learning to read, with each new discovery adding another page to the extraordinary story of our ever changing planet. The quiet laboratories where these frozen messengers are studied have become temples of discovery, where scientists gather around cores that glimmer with an ethereal blue light. The color that comes from ice compressed under such immense pressure that it has expelled all air bubbles except those tiny, perfect spheres that hold ancient atmospheres like precious gems. Each laboratory maintains temperatures so cold that researchers must wear special gloves just to handle the samples, yet their dedication to unlocking these secrets burns warm and bright. When a new core arrives from the field, it's treated with the reverence reserved for the most precious artifacts. Every surface is documented, every bubble photographed, every layer measured with instruments so sensitive they can detect changes in thickness smaller than a human hair. The cores are stored in freezers that maintain temperatures far below anything found in nature, creating artificial environments colder than the polar regions where the ice originally formed. The most experienced ice core readers develop an almost supernatural ability to interpret what they see, tiny variations in crystal structure that reveal ancient storm patterns, microscopic inclusions that tell stories of volcanic ash carried by winds that blew thousands of years ago, subtle color changes that mark the boundaries between seasons that occurred when civilizations were rising and falling on the other side of the world. Some cores contain layers so thin they can barely be seen with the naked eye, yet each represents a full year of Earth's history compressed into a space thinner than a sheet of paper. These gossamer layers require special lighting and magnification to study, but they reward patient examination with extraordinarily detailed records of ancient climate variations, revealing patterns that operated on scales from individual storms to century-long climate cycles. The process of extracting gas samples from trapped air bubbles has been refined to an art form. Researchers use techniques borrowed from archaeology and forensic science, handling ancient air with the same care that might be given to evidence from a crime scene the moment when an ancient bubble is released and its contents analyzed represents a direct connection across geological time, like shaking hands with the atmosphere of the distant past. Certain ice cores have become legendary among researchers, not for their age or depth, but for the extraordinary stories they tell. One core from Greenland contains evidence of a massive volcanic eruption that created a winter lasting several years visible in the ice as a dark band that marks a time when crops failed across the northern hemisphere and civilizations struggled to survive. Another core reveals evidence of an ancient forest fire, so vast it darkened skies across entire continents. The chemical conversations recorded in these frozen archives reveal Earth's climate system to be far more interconnected than early scientists ever imagined. Changes in ocean currents affect atmospheric circulation, which influences precipitation patterns, which alter vegetation growth, which changes the chemical composition of dust blown onto ice sheets, creating feedback loops that can amplify or dampen climate changes in ways that are still being discovered. Reading ice cores requires understanding not just what happened, but when it happened with precision that challenges the limits of scientific measurement, establishing accurate chronologies for cores that span hundreds of thousands of years requires combining dozens of different dating techniques, each with its own strengths and limitations. The most skilled chronologists can determine the age of ice layers to within a few years, creating timelines more accurate than many historical records. The deeper sections of cores often contain surprises layers that don't match expected patterns, chemical signatures that suggest unknown climate phenomena, or evidence of events so rapid and dramatic they challenge our understanding of how slowly climate systems are supposed to change. These anomalies become the focus of intense study, often leading to discoveries that reshape our understanding of how Earth's climate operates. Some of the most valuable information comes from comparing cores drilled thousands of miles apart when the same event appears in ice from both Greenland and Antarctica. Researchers know they're looking at something that affected the entire planet. Simultaneously, these global signatures help distinguish between local weather variations and true climate changes that altered atmospheric circulation worldwide. The microscopic world preserved in ice cores continues to yield new discoveries. As analytical techniques become more sophisticated, ancient bacteria, viruses, and even fragments of genetic material from long extinct species have been found in ice that formed during the last ice age. These biological time capsules provide information about ancient ecosystems that no other source can match, revealing how life adapted to climate conditions that no longer exist. Studying ice cores has revealed that our current climate represents just one possible state among many that Earth's atmosphere can adopt. The cores show evidence of atmospheric compositions and circulation patterns so different from today's that they seem almost alien, yet they all occurred on the same planet we inhabit now, suggesting that climate stability may be more fragile than we once believed. The technology for drilling ice cores continues to advance with new techniques that can extract samples from ever greater depths while maintaining their pristine condition. Specialized drilling fluids prevent contamination, while diamond-tipped bits can cut through ice that has been compressed under enormous pressure for hundreds of thousands of years. Each technological improvement opens new possibilities for discovery. Some ice cores contain evidence of cosmic events that no human ever witnessed, massive solar storms that altered Earth's magnetic field, asteroid impacts that filled the atmosphere with debris, and even changes in cosmic radiation levels that suggest our solar system passed through regions of space with different properties. These extraterrestrial influences on Earth's climate remind us that our planet exists within a larger cosmic context. The preservation of seasonal patterns in ice cores creates a kind of ancient calendar more reliable than any human record. Spring dust storms, summer organic matter, autumn precipitation, and winter's clean snow all leave their distinctive signatures in the ice, allowing scientists to reconstruct not just annual averages, but the actual rhythm of ancient years and how seasonal timing has changed over millennia. Laboratories around the world maintain vast freezer facilities filled with carefully cataloged ice core samples, each segment labeled with precise depth measurements, dates, and chemical compositions. These frozen libraries represent one of humanity's most valuable scientific resources, containing information about Earth's climate history that exists nowhere else and can never be replaced if lost. The international database systems that track ice core information have become models for scientific cooperation. Researchers anywhere in the world can access data from cores drilled in the most remote locations, sharing discoveries and techniques that accelerate understanding the ice cores belong to all of humanity, representing a shared heritage of climate knowledge that transcends national boundaries as you drifted deeper into the realm of dreams. Tonight, perhaps you'll find yourself walking through these frozen archives, touching ice that formed when your distant ancestors were discovering agriculture or metalworking or writing the cores. Connect us to deep time in ways that make the brief span of human civilization seem like a single breath in Earth's long conversation with itself. The patient accumulation of ice over hundreds of thousands of years creates records of such extraordinary detail that scientists can sometimes identify individual weather events from the distant past, a particularly severe drought, a volcanic winter that lasted several years, or an unusually warm decade, all preserved with clarity that rivals modern meteorological records. Some cores contain what researchers call climate flickering periods, when Earth's climate system seemed unable to settle into any stable pattern. Temperatures oscillating wildly, precipitation shifting unpredictably, atmospheric composition fluctuating like a radio signal searching for the right frequency. These unstable periods often preceded major climate transitions, suggesting that flickering itself might be a warning sign of impending change. The chemistry preserved in the deepest sections of cores reveals atmospheric conditions from times when Earth was so different it barely resembles the planet we know: ice ages, when massive glaciers covered continents, warm periods when forests grew in what is now Arctic tundra, and atmospheric compositions that supported ecosystems unlike anything alive today. Modern ice cores, the layers forming at this very moment, will someday tell future scientists about our era. They will see the chemical fingerprint of industrialization, the spike in greenhouse gases that marks the Anthropocene, and perhaps evidence of how our civilization responded to the challenge of climate change. We are all contributing to the ice core record that future generations will study. The stories whispered by ice cores remind us that Earth operates according to rhythms and cycles that dwarf human experience. While we measure our lives in decades, the ice records changes that unfold over millennia, revealing a planet in constant motion, constant change, constant adaptation to new conditions. Tonight, as sleep embraces you, let your mind wander to those remote ice sheets where snow continues to fall, carrying with it the chemical signature of today's atmosphere, destined to become part of the frozen library that future scientists will read to understand our time. The ice cores teach us patience, humility, and wonder at the intricate beauty of our ever changing planet. Somewhere in the darkness of polar night, researchers work by artificial light, extracting cores that bridge the gap between deep time and the present moment. Each sample a messenger from ages past, carrying stories of climates that shaped the evolution of life itself and continue to influence the world we inhabit today. The ice remembers everything, and in its patient silence lies the key to understanding not just where we've been, but where we might be going in the grand epic of Earth's climate story. We are both authors and characters, writing new chapters while reading the ancient wisdom preserved in these frozen libraries of time. The final secrets of ice cores lie not in what they preserve, but in what they teach us about impermanence itself. As you lie there in the gentle embrace of approaching sleep, consider this. Every breath you take, every molecule of carbon dioxide you exhale into the quiet darkness of your room will eventually find its way into the global atmospheric dance. Some of it may drift across continents, rise high into the polar skies, and fall as snow onto the ice sheets of Greenland or Antarctica. Years from now, perhaps decades or centuries hence, that very breath you're taking right now will become part of a frozen layer, compressed and sealed away in ice that future scientists will study with instruments we can't yet imagine. They will read the chemical signature of our time, like archaeologists deciphering an ancient language, piecing together the story of how we lived, what we burned, what we grew, and how we changed the very composition of the air itself. This is the beautiful paradox of ice cores. They are simultaneously records of the most ancient past and prophecies of the deep future. Every core tells two stories: the climate that was, preserved in crystalline perfection, and the climate that is becoming, written layer by layer in the accumulating snow of polar regions. We are living between these stories, in the thin present moment, where past becomes future, where memory transforms into prophecy. The researchers who study these frozen archives often speak of a peculiar sensation that comes from handling ice that formed before human civilization existed. There's something profoundly moving about holding in your hands a piece of frozen water that fell as snow when saber-toothed cats prowled through landscapes that no longer exist, when the ancestors of every living thing were adapted to atmospheric conditions we've never experienced. Yet perhaps the most remarkable discovery from ice core research isn't about the past at all, but about the future. These frozen libraries have taught us that Earth's climate system, for all its apparent stability, is capable of changes so rapid and dramatic that they redefine what we thought was possible. The ice whispers warnings about tipping points and cascade effects, about the delicate balance that keeps our planet habitable and the surprising speed with which that balance can shift. In the deepest, oldest sections of the longest cores, scientists have found evidence of climate states so different from our current world that they seem like records from another planet entirely. Atmospheric compositions that would be toxic to most modern life, temperature patterns that would make agriculture impossible, precipitation cycles that would render our current ecosystems unrecognizable. Yet somehow, life persisted, adapted, and eventually flourished again. This resilience recorded in ice gives us both hope and humility. Hope, because it shows that life finds ways to survive even the most dramatic changes. Humility, because it reminds us how temporary our current climate stability truly is, and how quickly the conditions that support our civilization could change. As your breathing slows and sleep approaches, let your mind drift to those patient ice sheets where this ancient conversation between earth and sky continues. Tomorrow's weather will add another thin layer to archives that have been building for hundreds of thousands of years. The storm clouds gathering somewhere in the distance, the gentle rain falling on distant continents, the snow beginning to accumulate on remote polar plateaus. All of it will become part of the frozen record that connects our brief moment in time to the vast sweep of planetary history. The ice cores have taught us that we are not separate from the climate system we study, but part of it. Every decision we make, every breath we take, every fire we light becomes part of the atmospheric story that will be preserved in ice for millennia to come. We are writing the next chapter of Earth's climate history with our very existence, adding our voices to the ancient conversation between land and sea and sky. In the gentle darkness of your room, you are connected to these frozen messengers across vast distances and impossible spans of time. The oxygen you breathe once bubbled through ancient oceans, drifted through prehistoric atmospheres, and was exhaled by creatures that lived millions of years before you were born. The carbon in your body has been part of countless other living things, has been dissolved in ancient seas, has been locked away in ice and released again in an endless cycle of transformation. So rest well tonight, knowing that you are part of this grand story, this planetary conversation that has been unfolding for billions of years and will continue long after we are gone. The ice cores remind us that we are temporary custodians of an atmosphere that connects us to every living thing that has ever breathed and to every living thing yet to come. Somewhere in the polar darkness, snow continues to fall, carrying with it the chemical signature of our time, preserving it in crystalline perfection for future generations to discover. The ice remembers everything, our triumphs and our mistakes, our innovations and our impacts, our brief moment of consciousness on a planet that has been dreaming in ice and stone for eons beyond counting. Sleep peacefully, dear listener, cradled by the knowledge that you are part of something infinitely larger than yourself, connected by invisible threads of chemistry and time to every snowflake that has ever fallen, every breath of ancient air preserved in polar ice, every whispered secret that the frozen archives continue to hold. The ice cores will keep their vigil through the night, patient guardians of Earth's memory, faithful recorders of the endless dance between our planet and its ever-changing sky. And when you wake tomorrow, the story will continue, written in ice and air and the quiet persistence of snow falling on distant glaciers, adding another page to the most extraordinary library ever created, one written not in words, but in the very substance of our world itself. Sweet dreams, fellow traveler through time. The ice remembers, and in remembering, connects us all.